In Unit 5, it's entitled Spring, Sprang, Sprung. It says success is how high you bounce when you hit the bottom from George Patton. So the learning goals for this particular presentation are that you identify the factors that affect elastic potential energy. You should be able to relate work and elastic potential energy, just like we've been doing for all of these things. And you should be able to use the equation elastic energy is equal to 1 half kx squared. So what we already know. We know that energy can be stored as potential. In the last presentation, we talked about position relative to Earth, and we said that an object can have gravitational potential energy based on the fact that it's high above the surface of the Earth. We also know that work can be done on a spring and it must be stored. What we learned in the lab. We learned that suspending a greater amount of mass resulted in a greater force on the spring, and in fact, expanded that force actually stretched or compressed the spring a great deal. So, spring, sprang, sprung. Whenever you graph the relationship between force and displacement, you can get this right here. You have force and displacement. And whenever you look at it this way, you're trying to figure out what the work is in this particular case. We already know that actually it should be, displacement and force. Whenever you do this, you should get that the slope is the spring constant, or the K value. So the more force you have to exert in order to stretch the spring, the stiffer the spring is. We say that thing has a higher spring constant. Now, whenever we're trying to figure out what the energy stored is, the energy stored is going to be the force times the displacement. Well, that's how we calculate work. Work is force times displacement. But the problem that I run into for a spring is the fact that when you look at it, there is, at this particular point, the force was not always this value in order to get to this displacement. Instead, what we have is the force increases in order to get to that particular point. So when I'm trying to solve for the work, I can't just do this force times this distance. Instead, what I get is the area under the curve. And whenever you get the area under the curve, that's where you get this 1 half of the force times the distance. Well, remember, you can relate this K value, right back to distance as well. And when you do that, that's why you end up getting a squared term. So the equation we get when you actually put all the math together, you'll see is this right here. This elastic energy is equal to 1 half kx squared. But before we do that, let's refer back to K. K is the measure of the stiffness of a spring. So you've probably played with a slinky before, and a slinky is really, really easy to stretch and compress. Because of that, its K value, or its spring constant, is very, very, very low for a slinky. You've also maybe seen a trampoline spring, which is what you see here. A trampoline spring is very, very, very difficult to stretch, so we would say that its K value is very, very high for a trampoline spring. Now, the spring constant is measured in newtons per meter, and whenever you look at it, the spring constant does not change if you were to cut this thing in half. It's based on a per meter basis, so if you need this much, it's that many newtons per meter. This much, that many newtons per meter. So cutting the spring in half has no effect on the spring constant. So next, we talked about the equation already. The only thing that's new is we do have the spring constant, which does have to be measured with a spring scale and a meter stick, and it's a measure of the stiffness of the spring. It's in newtons per meter. We also have the elastic energy, which is measured in joules. Okay. Change in position is delta x, so this is like another way of saying that the displacement. So we have the conservation of energy. We know that the work done compressing on a spring is equal to the elastic energy stored in a spring, and because of that, we can say that conservation of energy is hell. So let's look at a couple of examples. The first one says how much energy is stored in a 64 Newton per meter spring that stretches 35 or 0.35 meters. So I'm trying to figure out what the potential energy elastic is, and I can say this right here is my K value. I know it's my K value because of the units. It's in newtons per meter. This is my displacement value, so I can say it's 0.35. Whenever you take these things, you can put them in the equation. Potential energy elastic is equal to 1 half kx squared. So whenever you plug this in, you end up getting 1 half of 64 times 0.35 squared. Now only the 0.35 is squared, not the whole thing, just 0.35, and when you put this in, you end up getting a potential energy elastic of about 3.98 joules. Next it says what is the spring constant? So in this case I'm looking for K of a spring that compresses 0.4 meters when 1200 joules of work is done on it. Now remember, whenever you do work on a spring, that energy has to be stored as elastic energy. So another way of saying this is that the work is equal to, I'm going to say EPE this time, it's just another way of saying elastic potential energy, is equal to 1200 joules. So whenever you do this, you also have a displacement of 0.4 meters. You can use the equation EPE is equal to 1/2 kx squared. You can plug in your numbers as 1/2 k 0.4 squared is equal to 1200. Whenever you multiply this out, you end up with a k value of about 15,000 newtons per meter.